Hi folks, this is Mr. Bergman. Today we're going to start a new unit. Unit 9. That's 9. 9 big ones. 9 out of 10. There's only one more to go. We're going to start talking about solutions. And I have my vitamin water here. And my vitamin water is a solution. Tastes good. Kind of has a sweet taste. Why do you think it has a sweet taste? It has a sweet taste because there is sugar dissolved in the water, in the vitamin water, including other vitamins and other flavorings. So this is a solution. This particular bottle has several things in it. In fact, if I read the ingredient list, where's the ingredient list? It contains, somewhere, vapor distilled water. Water? Water is considered the solvent. And the solutes are cane sugar, crystalline fructose, citric acid, calcium lactate, whatever it says on the label. So those are what we call the solutes, and together they make a solution. So we're going to focus on solutions in this unit. So let's get at it. Alright, now back on the screen here, we've got solutions. So let's learn about solutions. Podcast 9.1, we're going to talk about polarity and solvation. Okay, so this is an important thing. And we're going to talk about some surface properties. Notice I have some, what they're called, skeeter bugs. All right. Surface tension is the inward force causing the surface area of a liquid to minimize. All right. So, if you look at these skeeter bug guys, they're actually kind of like walking on water, aren't they? Isn't that kind of cool? All right. And if you want to reduce the surface tension, you can have a device called, or not a device, but a substance called a surfactant. All right, everybody say surfactant. Say it all right. All right, you must say surfactant. Surfactant. Isn't that a cool word? Surfactant. Soap is an example of this, and it can reduce the surface tension, and then the skeeter bug may or may not be able to walk on top of the water. Some things have high surface tension. Water has a very high surface tension, hence they can walk on that. And you can see them kind of blown up here. They're actually walking on the water, and you can kind of see that the water kind of beads up when you do that. Another good way to picture this is a water droplet on a leaf right here, and it's made a perfect sphere. It's just so cool to see this illustrated. And actually, let's do something else on the video monitor. Alright, so what I've got is I have a penny. As you can see the penny, the shadow out there. And there's the old Abraham Lincoln. And I have some water that I'm going to place onto the penny with a little dropper thing you can see. And the question is, how many drops can I place on the penny? Now, if you look there, I've got one drop. But do you notice how it beads up? All right, that's one drop, 2 drops, 3 drops, 4, 5 or 6, 7, 8, 9 or 10, 11, 12, 13. Let me stop there for a moment. Lucky 13 or unlucky? Notice how the water has beaded up onto the penny. And this is due to the high surface tension of water, and the high surface tension is due to the type of bonding. And if you remember from the last unit, water is held together by hydrogen bonding. And hydrogen bonding, that another force is very particularly strong. So 13, and you see I can keep beating this up, 14, 15, 16, 17, 18, 19, 20, 21. You see I can get quite a few, and it's all beaded up. Now I actually need to refill my water deal. Okay, 21, 22. It's beading up. This works. I've got 27 drops of water on top of that tiny little penny, and it's way overflowed. That is because of the high surface tension of the water. I just think it's just really cool. Eventually, oh, it spills. As you can see now, it's making a mess. It's finally like 28 or 29 from this particular dropper. And so I think that illustrates kind of what we're talking about this surface tension. Now, if you were to try this with other chemicals, like, say, alcohol, which does not have, not held together by hydrogen. Actually, there's some hydrogen bonding in that particular most alcohols, but not enough because it has lower surface tension. It would not beat up at all. So it's a pretty cool way to illustrate the idea of surface tension. Okay? All right, on to page 3 in our composition books. What is this solution process? Now I want you to take a look at the picture over on the right. And what I have is I have some salt. You know, there's some salt over here, and it's being dumped into a cup of water, right? All right, now there is a variety of a solution called an aqueous solution. Everybody say aqueous. There you go. All right, and an aqueous solution is a homogeneous mixture of a solute, and the solute is water. Hold on. Of a solute and water. Water is the solution. We'll get some terms defined here in a couple of minutes. All right. Now, in a solution, there are sort of 3 parts, if you will. There's the solute, that's the dissolved particles. So in this particular case over here, the dissolved particle will be the sodium chloride, or the salt. We're putting salt into water in that particular picture. You could dissolve sugar in water, like in my vitamin water a minute ago. And then there's the solvent. Everybody say solvent. The vent of the solvent, is what's considered the dissolving medium. And so in the case over here, water is the solvent. And because this is water as the solvent, it's called an aqueous solution. So for example, you could write NaCl, and if you wrote parentheses AQ, that means the salt is dissolved in water, AQ. Okay? And solvation is the process by which something dissolves. Now, don't get that confused with salvation. That's kind of a whole different ballgame, isn't it? Okay. Excuse me. So the process. So as the salt dissolves in the water, it's said to solvate, or you could just say it dissolves, but the process by which it happens is called solvation. So we can see a bigger picture of that. Exciting. All right. So actually, let's do one more thing here before we go to podcast 2. When something dissolves, let's take an example of salt in water. That's a good example. If I were to take salt in water, salt sodium chloride is a ionic compound. Remember, we talked about ionic compounds in the last unit, Unit 8 on bonding, right? And the sodiums and the chlorides are connected to each other in a pattern. I'm attempting to draw this. You should draw this as well. The little one, I think, is the chloride, and the big is the sodium. Is that right? No, the chloride is the bigger one. I got it backwards. So basically, if you were to take a crystal of salt and drop it into water, and if you recall, water has this Mickey Mouse type shape going on, the bent 104-degree angle. What happens is the water comes into the sodium, and it comes and it pulls away, and it surrounds, it breaks this bond. If you recall, this ionic bond here is very strong. Very, very strong. But if enough water molecules they can grab, what happens is they kind of face themselves, or face the ions. They break apart the salt. And then this right here would be positive, so this would be a sodium atom, right, or ion right here, and they surround it. And so actually when you like taste salty water or things that taste salty, you're actually tasting the ions of the sodium. So I think that kind of helps us get an understanding. It breaks it apart. So when something dissolves, it's broken apart, separated into its ions. So that's this piece right here that is now here. And then the chlorides would actually be surrounded, but they'd be surrounded in a different fashion where the hydrogens would be on the opposite sides. It has to do with the where the charges are. So if you did that part, some people have done that part of the unit and some not. Now this is the chloride right here, and this is the sodium ion right here, and it surrounds them, and they've separated. So the sodiums are no longer connected together, so that piece of salt, that salt crystal that you had, has all broken apart into individual ions. Well, folks, that's the end of podcast 9.1. We'll see you in Internet Land. Bye.